So Arrhenius' theory works really well when you talk about acids and bases that are in aqueous solution. The idea that, hey, Arrhenius model, acids break up into hydrogen ions, bases break up to hydroxide ions. Some substances, though, very clearly display acidic or basic behavior despite not being an an aqueous solution. And some bases don't even include hydroxide at all. And so this is a little bit of a problem with the Arrhenius model. So in the 1920s, separately, Johannes Bronsted and Thomas Lowry, a Danish and a British scientist, came up with a different model, came up with the same idea, different places, for how acids and bases work. And so they noted something, that when an acid dissolves in water, it transfers that H plus to the water molecule to form hydronium. That happens every single time. And so they said, maybe that's not just a secondary factor. We talked about Arrhenius. We said, well, it makes the H plus ion, and then it just does join the hydronium. But Bronsted and Lowry argued that addition, the loss of a proton that is a hydrogen ion from one molecule to and had it join a different one, is at the heart of what makes acids acids and bases bases. This transfer is the key piece. So let's look at it. Bronsted-Lowry theory basically says this: acids are substances that can transfer an H plus ion or a proton to another substance, and so we call them proton donors. Bases are substances that can accept an H plus ion, and so are proton acceptors. Remember that we said that this H plus ion is really nothing more than just a bare proton, right? And so if a proton were to move, an H plus ion were to move from one compound to a different, or one joining up of atoms into a different one, and so one substance to a different one, then this would be a transfer of a proton. And so acids are proton donors. They give away protons. They give away hydrogen nuclei. Bases are substances that can accept them, and so they're proton acceptors. So let's look at what this might look like. So down at the bottom here, we have hydrochloric acid and water. So hydrochloric acid right here, you can see you have a chlorine and we have a hydrogen. They are covalently bonded because chlorine needs one more electron, has to fill its octet, and so hydrogen needs one more to fill its octet as well, and so they have a shared pair that's right here between the hydrogen and the chlorine. But what happens in this particular case is that the hydrogen says, hey, I could go over here and jump toward the water. I could defect it in some way. You could say this hydrochloric acid would donate that proton over to the water. You can see it over here. That it's jumped over to this side. Now the hydrogen left its electron behind, right? So now it's chlorine minus, right? It's a chloride ion right here. But what's happened is the hydrogen, as it jumps over, has that empty shell, that empty 1s orbital. It overlaps with one of the full orbitals in the water and forms that coordinate bond that's in there. But in a sense, what's really happened is the HCl has donated a proton to the water, turning it from water into, note the 1, 2, 3, hydronium, H3O plus, and it's plus because it gained a proton, it gained a positive charge in here. And so what Bronsted and Lowry would argue is they would argue that this hydrochloric acid, because it donated a proton, is going to be an acid. That's why it's an acid, because it donated a proton. And that the water in this case is a base because it accepted a proton. Acids are proton donors, bases are proton acceptors. And so that's the argument that Bronsted and Lowry made. So let's look at a case where Bronsted-Lowry works but Arrhenius doesn't. Ammonia, NH3. If you were to taste ammonia, it would be bitter. If you were to, slide around your fingers, it would be slippery. If you stuck it into a piece of litmus paper into ammonia, it would come out as being basic. So it clearly acts like a base. It's a base in the way it acts in every single way. But notice, no hydroxide, right? No hydroxide, which means the Arrhenius method would say can't be a base, because how can it break up into hydroxide when it has no hydroxides in it? Okay, so here is what Bronsted-Lowry said. Okay, well, it can accept a proton from water. So let's suppose that we had a reaction ammonia plus water, like this, and we can see them down below. So we have the ammonia down here, 3 hydrogens, 1 nitrogen, but that nitrogen does have this one lone pair of electrons that are in the one orbital it has filled up. And so what will happen is this hydrogen right here will jump, or at least the hydrogen ion will jump as a proton. It donates that hydrogen proton, the water donates the hydrogen proton over to the ammonia. Now that that happens, it's no longer ammonia, because it has gained a proton. So instead of being NH3, it's now NH4, but because it gained just a proton without the electron, it left that back behind at the water, it's NH4 plus, and now it's no longer water, because the water, look down at this here, it's lost its hydrogen, but it kept the electron from it. So as a result, it's just going to be hydroxide. So this would explain where the hydroxide comes from, is it doesn't come from the ammonia, it comes from the fact that it's sort of left over afterwards. But the Bronsted-Lowry argument here is that, hey, what's happened is that the ammonia is going to be the one that accepts the proton. So it is going to be a Bronsted-Lowry base. The water molecule is the donor of the proton. So it's going to be a Bronsted-Lowry acid. And so that's the reason why ammonia is a base, because it's a proton acceptor. And in this case, the water is going to be an acid. And so that seems a little odd. Like, how could water be an acid? Especially considering that last time we said that water was the acceptor, and so there it's a base. So how does that work exactly? It's like water's a little bit of both here. So we'll get to that in a second here, but let's take a look. So Bronsted-Lowry theory argues that any reaction where a proton transfers from one substance to the other, from the acid to the base, is an acid-base reaction. So now we know what we said before, that a substance can be a Bronsted-Lowry acid in one reaction, but a base in the other one here. So we'll look at very similar to what we just did. So here, this first reaction we have here, we have water and hydrochloric acid, is that the hydrogen is going to jump from the hydrochloric acid. The hydrochloric acid is going to donate the proton. So they're sort of showing it right here, so jumping over there. So it is going to donate the proton to the water, and so that makes the HCl is the donor, and so since it's the proton donor, it's the acid. And since the water accepts, it's going to be the base. But in our other case here, we have water on the bottom, looking down here, water on the bottom, and then NH3 ammonia right here. In this case, what's going to happen is that the proton is going to jump to the ammonia to form a coordinate bond there, and so when it does it, then the water is donating the proton, so the water is an acid, the ammonia is accepting the proton, so the ammonia is the base. And so water is sometimes a base and sometimes an acid according to Bronsted-Lowry theory. And so a substance like this that sometimes acts like an acid and sometimes like a base is called an amphoteric substance. And so there are a number of these that are out here. But so Bronsted-Lowry would basically make an argument that, you know, substances aren't acids by themselves or bases by themselves, but they're acids or bases in comparison with something else. Is that you really can't just say, hey, water is an acid, it is a base, it is neutral, is that it's neutral when it's by itself, it's a base when it's with hydrochloric acid, it's an acid when it's with ammonia, and different substances can act this way. So let's look at another reaction here. Let's look at hydrofluoric acid and water. So hydrofluoric acid is just HF. And so with this hydrofluoric acid, what's going to happen is we have HF plus H2O, is that hydrofluoric acid is going to donate the proton over to the water, leaving us with hydronium, H3O plus, and leaving us with a fluoride ion, because the hydrogen, it only donated the proton, not the whole hydrogen atom, so the electron from the hydrogen is left behind, leaving it as F minus fluoride. It has a nice full octet right there. Now, so very clearly here, because the hydrofluoric acid donated the proton, that is going to be our acid. And because the fact that the water accepted the proton, that is very clearly going to be our base. Now, take a look over on the right side, though. We've created a hydronium ion. This hydronium ion has an extra proton to it. Now, you know, couldn't that hydronium donate that proton? And fluorine, it's got a negative charge. I mean, that seems like it's like fit for taking a proton from something else. In fact, maybe it even would take the proton back from the hydronium, which would create a reverse reaction. We could have an equilibrium reaction where sometimes the water takes the proton from the hydrofluoric acid, and sometimes the fluoride takes the proton from the hydronium, going back the other direction. Now, in that case, because the fact that the hydronium is donating the proton, it is sort of an acid, and because the fluoride is sort of accepting the proton, it's a base. And so what Bronsted-Lowry theory basically notes is that anytime you have an acid-base reaction, what it creates are also acids and bases. They're called conjugate acids and conjugate bases. And so what basically happens here is that each reacting acid will have a conjugate base. Okay, so the HF, hydrofluoric acid here, that's our original acid because it's going to donate that proton to the base right here. But in the process of doing this, it leaves behind a fluoride ion. That fluoride ion is ripe for pulling off and taking a proton away from the hydronium, which makes it the conjugate base. It is the conjugate base of this particular acid right here. And the same way that this base that we have, that's H2O, that is going to accept the proton from the acid, from the hydrofluoric acid, when it accepts it, it creates this hydronium, which is a positive charge. It's going to be more likely to give away that proton, and so that makes it a conjugate acid, and so that the base has a conjugate acid that's with it here. And so these form pairs. We call these conjugate acid-base pairs, is that for every acid, it will form a conjugate base. For every base, it will form a conjugate acid whenever we have these types of Bronsted-Lowry reactions right here. So what if we need to find these? So how do you find what the conjugate base of an acid is? So pretty simple. You remove a single proton from it, right? Because that's what's going to happen here. So if I have HBr, hydrobromic acid, it's going to be an acid because the fact that when this reacts is that what should happen is it should probably look a little bit like this. We have HBr plus H2O. This is what the reaction would look like. It's going to donate that proton from the bromine to the water, creating hydronium, H3O plus, and then what's left behind? A bromide ion, Br minus. And so the conjugate, so for this acid, since that's our acid, because it's donating its proton, the conjugate base is going to be Br minus. Notice all that's happened here is we've taken HBr, gotten rid of the H, but then left the electron with it. So now it's got an extra electron, so it's Br minus. So that's sort of how that works. So the conjugate, the conjugate base of HBr is just Br minus. What about the conjugate base of H3P, hydrophosphoric acid? So for this one right here, it's going to do the same thing. It's got to lose a proton, so now it's going to be H2P, but because of the fact that it didn't just lose the hydrogen atom, it lost a proton, that electron's still there. So its charge is going to drop by 1. HSO4 minus. Now this is an ion, but it still works the same way. These polyatomic ions can also act as acids or bases. So this one right here, it's going to, since it says it's an acid up here, let's say it's going to, where's the question is what's its conjugate base? So it's going to lose a proton. So now it's going to be SO4. It's lost its hydrogen right here. The charge originally was a -1, but since it lost a proton, now it's going to be -2. That's just sulfate. And so in this case, this hydrogen sulfate polyatomic ion is the acid, and the conjugate base is just the sulfate ion. So similarly, if we have a base to find the conjugate acid, you add a single proton. So we have BrO3 minus, the bromate ion. So the bromate ion in this case is the base. Its conjugate acid is going to be the hydrogen with the bromate ion. So we had the hydrogen and the bromate. Let's take a look at what's going to happen charge-wise here. It originally had a -1 charge, and so since we're adding a proton, that's a +1. It cancels out. We just end up with bromic acid, HBrO3, for what we have here. HPO42 is going to be our base, so our conjugate acid would happen because it's going to accept a proton. If it accepts a proton, it's now going to be H2 instead of H, PO4. It was originally -2, but now since we've added a proton to it, it's just going to be minus right there. So H2PO4 minus dihydrogen phosphate is going to be the conjugate acid for hydrogen phosphate, HPO4 minus 2. NH2 minus. So that's our base. So then it's it's going to accept the proton, turning it into NH3. Since it's a negative charge and we're adding a proton to it, it just cancels out. We just have NH3, just ammonia. So ammonia would be the conjugate base of, the conjugate acid of the base NH2 minus. H2O, water. Hey, this should be familiar here, is that, so in this case, this is acting like a base, so to become an acid, it's got to accept, the base is going to accept the proton, forming H3O, but since we added a proton, it becomes a plus. Hey, that's just our hydronium ion. And so whenever water is acting as a base, then the conjugate acid would just be hydronium.